Thank you. Thank you for the invitation. And I will start with one or 2 points. Like the first point, I think, is like the primary problem is not AI, using AI for solutions and so on. The primary problem is policies. It's a policy problem. It's a problem of political economy. That's why I also appreciate Liam's talk yesterday, which targeted like the political economy with AI methods. So I want to put that as a framing so that we don't overestimate what we can deliver. The second thing is that I think we need a lot of integration of AI methods with other methods, because that leverages the full potential. Other disciplines have a detailed understanding of mechanistic relationships, and that can make a lot of use. And especially one of the issues is that we not need a lot of dynamic models to actually see how transitions to more sustainable systems can happen. And a lot of data that we have are more static, so we really need to connect it with some sort of dynamic modeling. This is the full idea. What I'm presenting, I'm focusing on cities here. The idea of like finding urban transitions that really fulfill some of the sustainability objectives. Of course, I'm coming from a climate change community. It's focused on zero carbon cities. Here's what I see as important disciplines. We want to go very specific into spatial scope. We can make use of very detailed available remote sensing data. There are a lot of data science approaches there now and also like complex system science. Urban planning has to offer a lot, and urban economics has a detailed understanding of the economic relationships within cities that are actually quite useful. And I think they are underrated because they're a little bit closeted community. Here is some of our previous current understanding of what can be used for. Like one of the typical problems that we have is that as a climate change scientist, we are interested in the global level of emissions, and any given city has only a tiny amount. So what's the contribution individual cities can make, and like how does it scale? Like as an urban researcher, you will always say, oh, every city is different, and it's true. But then also what's true, some cities are more similar to each other than others. And you can solve this, or you can tackle this at least conceptually, by building typologies. So this is our approach on global cities, 274 cities, representative in terms of income and size distribution and continental distribution. And we just use a regression tree to endogenously classify the cities according to drivers of greenhouse gas emissions. So below here you find 8 types of cities classified according to drivers of greenhouse gas emissions. And it's non-trivial in the sense that some clusters, for example, I think 13 and 14 basically have an equivalent amount of energy per capita, but they have different drivers. Like type 13 has relatively high income, low gasoline prices, high population density, and type 14 has high income, high gasoline prices, and a low amount of HDD, so not much heating is derived. So you can see also like this, I mean, it's quite simple, of course, much more drivers. So it's like the data that we had here. But you can see that economics play a role. You can see that urban form plays a role in terms of population density. Economics play a role in terms of fuel prices and policies. So this is obviously a key policy driver, and I come back to that. And the local climate plays a role, not surprisingly. Can boil that down to a much more specific spatial scale. This is England and specifically London. You can develop typologies of residential greenhouse gas emissions. Top left, these are 15 different types. The key driver is here is actually population density, not income. It becomes much more important if you go into residential emissions. Household size is important. Income levels become important at a later stage, and heating system, HED, like these kind of issues become important when you go down into the scale. You can, so this is for 7,000 English districts, and London, as you probably know from sociology studies, London is very different from England. We see the same in terms of energy types. We can relate it to the left bottom. This is centrality types. So centrality types actually correspond to basically the types of residential emissions relate to centrality in a good pattern. And also these down to the right are lifestyle groups, and they can be statistically related. So actually we even know about lifestyles. There's a lot of data available, and it's really like policy informative, because you can target for example, in terms of like heating system, in terms of like housing conditions, and a few other variables what you can do. So it's like it's coming from the top. It's not starting from the middle building level, but it goes into that direction. So, and then a third, like our second big approach is to actually make use, and that's something that Max also presented yesterday, to make use of big literature data. So what we can do is to extract all papers on cities, for like specific cities, using a list of 4,000 something cities, like individual case studies basically, and we can extract these case studies. Here is just a mapping of that, and then use the information that's in case studies to code that in terms of like bottom-up information, and then we match it actually with the top-down information that we have from data scientific approaches. So we are developing more and more data, like a more elaborated database of global cities with about 200 variables, and we're trying to get more and more complete on that. So, but what I want to talk about is like how to get a little more systemic perspective into that. So this is just a static data science basic here, and to look into the co-evolution between the human and planetary system, looking specifically at the role of cities down there. So like they as cities as the intermediate between human and the Earth system, and how to make use of transforming cities to actually have the Anthropocene trajectories a little bit more sustainable. So like there are a little bit more complex interactions, not only the city, it's like not only the planet, it's like four dimensions of the planet: lithosphere, hydrosphere, atmosphere, and biosphere. And of course, in all of that, there are interactions. Like just to go quickly through that, lithosphere is like really the resources that you extract, and it's an exponential increase, mostly for cement and asphalt. Then you have the hydrosphere interaction, like via climate change, you have an increase in sea level rise, and that interacts with cities at, for example, I think more than 128 UNESCO heritage sites are threatened by sea level rise, and Venice is basically the first one that actually suffers now already from that. Then obviously you have the atmosphere interaction with the climate change, with greenhouse gas emissions. These are the increasing greenhouse gas emissions coming from cities, and the gray one, I think I have another slide on that. The gray one is really like the emissions that come from building the environment here, and it also clarifies like what you build now has impact on the future. Then you have the land interaction, which is really the urban expansion and the interaction with the agricultural system. And then you have the feedback from the atmosphere on the city level via heating, like basically lethal, deadly levels of heat that you can codify again on individual city level for different climate scenarios. So, but coming to the solutions, what are they? Like at first, it's like a normative question, of course, what are the goals? And I think we need always explicit discussions on that. We cannot just say, oh, we find like we apply a method, something. We have to be specific about the normative dimension about that. If we don't, then we actually hiding the normative thing, because there's always some normative dimension in there. So like one good starting point are the SDGs, because these are politically agreed targets that actually include a lot of detail, more than 170 indicators, 17 goals. Like in the specific thing that I'm talking about the mostly urban mobility system, of course, like it's zero carbon is dimension. Then like if you go into the first 7, 8 SDGs, these are all about human well-being. So human well-being is relevant. And if you go into the literature of well-being, it's basically always about accessibility to service. So you want to have like an inclusive transportation system that enables accessibility to a lot of facilities. Of course, it's only part of the accessibility problem, but it's a major one. And then what is actually not coded in SDGs, but what we are talking about, and also heard yesterday evening, it's really about like data control, like who has the control, what are the institutions here, and the institutions are actually established, but the question is, and some of us are quite motivated into looking alternative institutions of data governance, that is important both for academics and science, but also, of course, for the users. So that translates here into what I call radical shared mobility scenarios, which is really like how do we have motorized transport that is hyper efficient and hyper convenient for users and very inclusive. The second one is the bike cities, which also promotes the active physical activity here. And then the urban scale data governance question related to that. I won't go really into details. I just want to suggest here like what are the points to go forward. So system science, Donald Meadows put into a paper like 12 leverage points of how to change a system. And it's to some degree surprising. I will only go into 3 of the leverage points because I think these 3 ones that I will present are the most important from an urban perspective here. So, urban systems, but in the interaction with digitalization and big data. The first one is physical structure. Physical structure is only ranked number 10 by Donald Meadows. Why is only ranked number 10? Because she says most physical structures are already there, so you can't change much. Now, for urbanization, we are living in the center of urbanization, and the urban structure for about 3 billion people is only built now in the next 1 or 2 decades. And that will make a major difference. The physical structure is a major one. This is just an example. You can compare Atlanta and Barcelona. They have about the same, this is actually old data, 1990 from World Bank, really good stuff. 1990, factor 10, they have the same income per capita, they have the same population, they have factor 10 difference in size, they have factor 10 difference in greenhouse gas emissions. So like you can see that, and it's mostly physical structure really that relates to that. And I said that what we build now will translate into future emissions and a lot of opportunities to actually change that. That's the blue one in terms of incentivizing future emissions. And we know from established assessments that there are a number of different properties that can be changed in urban structure, which is not only population density, it's also like land use planning, like especially mixed use. Then connectivity, street connectivity is a primary predictor of ensuring energy use, mobility, and accessibility in general for that. So that's very clear. We know it from a number of statistical studies and we know their relevance, but what we don't know is like their individual contextual relevance for specific things, and that's where big data and AI obviously gets in. We want to really assess on the spot for a given urban infrastructure what are the greenhouse gas implications, and it's always contextualized, and that's exactly where AI can be very helpful. So that's one of the projects, or perhaps the main project that we are really going into that. And of course, it's like hyper ambitious and it's like very difficult to get through all of that, but we have developed an infrastructure and we are now working on the first components of that to figure it out. So that's really Nicola is here, who's working on that. So second leverage point is the feedback loops. It's actually both positive and negative feedback loops. So basically, one of the problems is that we are accelerating everything in consumption, so we want to reduce that. And we need to reduce it in at least the metrics that we don't want to have, right? Like greenhouse gas emissions and energy use, or at least greenhouse gas emissions. So this is just like, and this is mostly coming from urban economics, like a structured diagram of the relationships between key variables and urban form and greenhouse gas emissions. The key thing here is, and this is very, very simple urban economics, like you have, it comes from Thun, Alonso Wood-Mills models. You have a central city where people are going to work, and they have to optimize 2 elements, like the utility of living, which is like they want to have large spaces possibly, and they want to minimize transportation cost. And it's empirically valid. This is what really people are doing. There are a lot of other factors that come in, of course, but this is valid. And what happens if you lower transportation cost, then of course you move further out. Because, and transportation cost means monetary cost and temporal cost. So you move further out, and then you have a larger living space available. This is very, very strong 1/x relationship. So it has a very, very dramatic implication if you actually modify the transportation cost only a bit, and that explains the large differences. Partially, there are other factors between Atlanta and Barcelona. A lot of path dependency issues in there, geographic factors in there, all true, but this is still nonetheless true. So this is just the the implications. You can look in only fuel prices. If you increase fuel prices, then you reduce emissions. If you have additional public transport infrastructure, you reduce it too. But the major one factor is fuel prices. This can replicate the energy use in global data sets of cities. And it can also explain sustainability windows, like very basically you optimize both for greenhouse gas emissions, reducing greenhouse gas emissions, and reducing air pollution and the receptor density of air pollution. And then, of course, you can look into more details, like geometric details. You want to have, for example, star-shaped cities. Why that? Because if you have just like everything, like if you just use it naively in terms of saying that you want to compactify everything, then of course you have a problem of complexification, which is congestion, air pollution, which can modify with electric transport again, but also, for example, access to green spaces that you want to have in when there are heat waves, for example. If you have star-shaped cities, you allow for high density cross-access that financially support public transit, while you have walking distance to green spaces. So that's something like Curitiba is doing, and it can be optimized also. And importantly, I'm not talking only here like some models, but this is verified also from data. Like basically, if you apply observed elasticities overall global city data set, you can see that only a fuel price increase to 1.7 euros or per liter gasoline will actually make a difference of 23% in future greenhouse gas emissions in cities, mostly in Asia, obviously. And these kind of, I mean, like the one important thing is that you can really use the topologies. These are the upper ones. You can use the topologies to explicitly see what kind of cities can have what kind of fuel price effect, for example, and relate it to the literature. That's what I meant before. There's two more leverage points. The new feedback loops, which could be a lot of information. So that's actually a lot of AI applications are doing that. You can have direct feedback on information on building scale, on mobilities, on solar roofing, which was mentioned before, which gives you a lot of information what you can do. And of course, that's very useful. And then we have the self-organizing capacity. We actually, this is like a bit of a meta point. You can use it for like very different kind of problems. But at the essence, you don't know what's going to happen in 30, 40 years. There's a high amount of uncertainty. But you know that what you want to have a lot of resilience in terms of like communities being able to make decisions. So you want to actually have the capacity of communities to deal with issues. One important thing is that you have system change if you have sufficient amount of committed individuals. That's very important to know. It means, and in our context, I think it's very important to look into digital institutions, into community data ownership programs, and like what I call like have been worked out for the Prime Minister's office in Israel, like an integrated data platform. So it really makes use of integrating all the mobility data that are around. And of course, as a governor, like the Prime Minister Office of Israel has the capacity to implement it, to mandate it just by law, basically. But the question is really what the design is. And you can look into, like, for example, data renting infrastructures. You can give community ownership. You can put it into like some sort of foundation with a public mission, which is not for profit, etc. Like all kind of things to look into that. And I think this kind of question, what kind of institutions we want to have, what we need, it's both important in terms of like our own access to data, but it's also very much important in terms of like urban governance for low carbon mobility, etc. So that's basically it. You can look into what kind of data you really want to have. Perhaps there's also dumb data that you want to throw away very quickly, or you want to shift it, that you actually have a very low amount of data issues. Yeah, I'm actually, okay, I keep this perhaps. This is like an envisaged model architecture where for different cities, one can do different kind of models, one more like AI-based planning models, others agent-based models on behavior and social change, others institutional models, and then somehow try to integrate those. And by this actually making an open source model platform and also a data framework that enables these kind of transitions. Of course, it's a long-term vision, and I think it would be really nice to have a lot of collaboration on this because any individual researchers can't do that. Thank you. Thanks.
Other questions?
Thank you, Felix, for the wonderful talk and vision on the problem. I would like to hear, I share completely the vision and the path that we have talked before. I would like to pick your brain on what would you tell to the community? One aspect I've seen in these three communities is that they focus on one layer and stay for it. And then so many people trying to do this, their own agent base and their own platform, etc. And what is bad is that lacking the big picture of your whole talk. Any insight, recommendations, or vision of how can we move forward to this collaborative environment in which we all share different resolution? If you think in physics, quantum mechanics, statistics, no, very different. But anything you can elaborate on these differences?
Yeah, very good question. I don't really know, but of course it's like some related to incentives that we have in academic environments. Like it's because we want to be we want to do it on our own, right? And I mean it's completely legitimate, but the question is like whether, I mean, also like in terms of like tools like GitHub Spaces, etc., to work collaboratively on projects, and where people with their specific expertise can jump in to accelerate really projects where, like, if you get newly into it, would take years. I think there's a lot of value into that, and I think perhaps one needs to have some experiments actually to figure out like where the incentives are working all right, that people, I mean, we don't have to change people preferences or like ambitions. That's not the point, but where the ambition comes together in terms of collaboration, and like perhaps there can be a few projects or ideas or like even online environments where there's some sharing of ideas, tools, etc.
Yeah, and I guess that a shared vision is the first step. You have to work in the same goal, I guess.
Yeah, so I was interested to see, I hadn't heard about this 1/x relationship between fuel costs and emissions. How does that change with like the electrification of transportation in terms of like the different components of those emissions? No.
Yeah, a very good point. I mean, electrification you really want to have for at least two reasons. I mean, probably more. But electrification in cities is very good because you reduce noise and air pollution also. So then you have the question of greenhouse gas emissions of electrification. There are, of course, like two issues: the energy embedded in the production of batteries and the electricity sourcing, right? So that basically most of that means that currently you have benefits, greenhouse gas emission benefits of electrification, but they're not so high. They will be probably high in 20 years with much higher renewable energy penetration in markets. So like, just like the bottom line. So it means the implication is that you actually can afford more urban sprawl with electrification. But then there are additional problems coming in. Like if you have currently 1.7 billion cars, if you have the market share moving forward, we have 3 billion cars in 2050, or 2.6 to 3 billion cars in that range in 2050, which means quite a lot of battery, lithium, or alternative technologies. Of course, technology are also working, but you have a waste problem, definitely. I don't know how big it is. It could be really big. It could be a lot of solutions into that. And then there's the problem of congestion, right? Congestion you have not solved by electric cars, and parking, for example, like it consumes so much time. So that's where I think there comes like radical shared mobility in. So you actually want to have highly flexible mobility, highly flexible and individualized mobility, but you can do it with shared pooled mobility. So where more than where few people share, like shared taxis or shared buses, where you can book on demand. And you never have any parking problems, so it saves you a lot of time on that. You don't have car maintenance problems, issues, costs related to that. And when everyone does it, you don't have any congestion problems anymore. So it's a really, it's a vision that it's a little bit not only greenhouse gas emissions, because you can solve it perhaps mostly technologically, but I think one should quite push for that, because if it just goes forward, you actually have 3 billion cars on the road, and then everyone is just stuck in their cars. And of course, autonomous car, you can read and work in there, but I don't think it's a desirable vision.
Let's thank Felix again. And